It's a beautiful day on the tropical beaches of Yokosuka, Japan. While you are sunbathing on the beach, off in the distance you see the USS Ronald Reagan and its carrier strike group departing from his home port at Yokosuka Naval Base. The deck of the Nimitz-class carrier is bustling with activity as thousands of sailors prepare to conduct joint flight operations in a display of force against growing hostilities from China and North Korea. On the flight deck, the dual engines of the F-35C roar to life. Electromagnetic launch rails accelerate the aircraft to flight. A great plume of fire erupts from the exhaust of the F-35, and within seconds, it has attained supersonic speeds. A century of innovation in engine design and manufacturing has enabled aircraft to operate in virtually every climate and terrain imaginable. And today, we will be discussing the inner workings of the modern jet engine. So welcome to Jet Engines for Dummies.
Shaktiman presents Jet Engines for Dummies.
Today, the F-35C is powered by a Pratt & Whitney F-135 engine, which is an incredibly complex feat of engineering, but let's take this to the million-dollar workshop and break it down. In order to fully understand jet engines, we need to understand not only their components, but also the airflow through these components. So let's start off by going over the basic components that make up a modern jet engine. Since these components do vary significantly between different types of engines, we will specifically look at the military turbofan, which is a type of engine that propels the vast majority of modern jet fighters and bombers. So let's jump right into it, and we will discuss these components from front to back. First up is the fan, which is pretty self-explanatory. It's just like a fan you would use at your home. It uses rotating blades to accelerate air from the atmosphere into the mouth of the engine. The next major component is the compressor. And this piece can basically be thought of as a fan just in multiple stages, which get progressively smaller in diameter as you go down the length of the engine. The combustor comes next. And this piece is responsible for generating the energy of forward propulsion, and it works by reacting the incoming air from the compressor with injected jet fuel. Behind the combustor, we have the turbines. The turbines can be thought of as reverse fans or a common pinwheel. Air flowing over the turbines causes the blades to rotate, and this process cycles the energy generated by the combustor back into the engine to power rotating components such as the fan, the compressor, as well as the life support and electronic systems on the aircraft. Modern jet engines tend to have multi-stage turbines, which are classified as high-pressure turbines and low-pressure turbines, and we will discuss these in more detail soon. The final major component in the engine stack is the nozzle. The nozzle is in charge of accelerating hot gases leaving the turbine out the back of the engine and producing thrust for the aircraft. So now that we've discussed the basic components of the engine, let's take it out back and fire it up. This will allow us to see how the air flows through these components and what this air is used for. So in order to fully understand how the air interacts with the major components of the engine, we need to understand the mantra suck, squeeze, bang, and blow. As unrelated as it may sound, we will make connections to the saying as we go. So to begin with, air is sucked into the front of the engine by the fan, which operates identically to a home fan, which pulls air into the back and accelerates it out the front. The air from the fan now has two options, either to flow down the center of the engine through what is called the core flow, or through the outer rim of the engine, which is called the bypass. Air entering the core will pass through all of the components which we described earlier, and will have work extracted from it by the turbines. However, the engine is required to spend fuel to compress and combust the core flow. On the other hand, however, the bypass, as the name implies, allows the air to bypass the major components of the engine such as the compressor and the combustor, and because of this, the engine does not need to expend fuel to compress or combust this air, but this bypass air still provides thrust or the forward pushing force for the aircraft. It is often a tricky engineering balancing act to determine the ratio of the air which should flow through the bypass compared to the air that should flow through the core. Air leaving the fan which goes through the core flow will hit the compressor next, which, as explained before, is simply the fan except much smaller in diameter and staged. From stage to stage of the compressor, the air is squeezed into a smaller and smaller sized channel. Modern jet engine compressors can have 10 to 15 stages in them, which can overall squeeze air, multiplying pressure as much as 30 to 40 times by the final stage. Now, the astute learner may be wondering why it is necessary to pressurize air in the jet engine to begin with. And we will answer this question soon as we move on to the next major component of the engine. The combustor is responsible for the bang. Compressed air is fed into the chambers of the combustor where fuel is injected and ignited by a spark. The superheated mixture of fuel and air wants to find a way out of the combustion chamber. And the options are either out the back end of the chamber or to the compressor where it came from, or a mixture of both. So to figure out why air flows the way it does, let's return to the question on why the air needs to be compressed when entering the combustion chamber. Well, the highest pressure inside of a jet engine occurs on the last stage of the compressor, right before the combustion chamber entrance. This means the air has no choice but to proceed out of the back end of the engine once combusted. This process occurs because air will always take the path of least resistance, and in the case of our engine, the air will avoid backflowing to the compressor due to the high pressure gradient which exists there. It will follow the low pressure gradient towards the back of the engine into the turbines. But before we can talk about turbine flows, we need to discuss the mechanical connections between the major components of the engine. As you can see in the diagram, there is a central shaft which runs down the length of the engine. All of the blades or rotating components are attached to the shaft. In modern engines, however, there are actually two concentric shafts. The outer, thicker shaft connects the high-pressure turbine or the front part of the turbine to the compressor, where blades are spinning at extremely high speeds and are exposed to a large amount of force. The internal shaft is thinner and connects the low-pressure turbine, or the back end of the turbine, to the fan, which experiences relatively low spin speeds and forces. So, in summary, if the high-pressure turbine spins at a certain rotations per minute, the compressor will spin at the same speed because they're on the same shaft. And the same principle applies for the low-pressure turbine and the fan. Anyways, let's get back to the turbine flows. High pressure, high energy, superheated air rushes out of the combustor and immediately collides with the first stage of the turbine, called the high pressure turbine. This air starts to spin the high pressure turbine and then proceeds to the second stage, the low pressure turbine, causing that to spin as well. Ultimately, these spinning high pressure and low pressure turbines are what end up powering the compressor and the fan of the engine in a perpetual cycle. So after the air flows over the turbines, it enters the nozzle. And the nozzle is responsible for blowing the air out of the engine, and it can be thought of as a tube which accelerates the air to supersonic speeds through the use of converging-diverging sections. The physics of converging-diverging nozzles is not in the scope of this video, but understand that it is a process by which slowish air coming from the turbine stages is accelerated out of the back of the engine, producing thrust. It is also important to note that in military applications, the back end of the jet engine also contains the afterburner. The afterburner operates by spraying fuel into the already superheated gases leaving the turbine. This fuel ignites on impact with the hot gases and provides that additional burst of thrust for the aircraft and leaves behind that signature plume of fire that fighter jets are famous for. And with this, we will conclude this episode of Jet Engines for Dummies. I'll see you in the next one. Shaktiman out.